Hello students, myself Parandina Patil. Now in ionic equilibrium chapter, this is second lecture. Now in this lecture, we are discussing the important topics. First, amphoteric nature of the water. Then ionizations of acids and bases. Dissociation of weak acids and bases. And then the law which gives a relationship between degree of dissociation and dissociation constant of acid and bases, that is that Ostwald's dilution law. We can discuss this one by one. Now let us first start with amphoteric nature of the water. What is mean by amphoteric nature of the water? So when you consider water, water is an used as a solvent. Water used as a solvent. We also know that water can be used as a universal solvent. Water is called as universal solvent. So water is a universal solvent. So why water is a universal solvent? Because it has a very high dielectric constant. It has very high dielectric constant. So what is mean by it has high dielectrical constant? So it has the ability, this solvent has the ability to break the electrostatic force of attraction between the ions of that salt and dissolve in it, and therefore this high value of dielectric constant belongs to water, and therefore water is a universal solvent. It observed that the solvent can be also categorized in the various parts, such as a protophilic solvent, then protogenic solvent, amphoteric solvent, and aprotic solvent. So solvent can be categorized in the four types: protophilic solvent, second protogenic solvent, amphoteric solvent, and fourth one is a aprotic solvent. Now what is mean by protophilic solvent? The examples such as water or alcohol or ammonia, these are the solvent called as a protophilic solvent because these solvent have a tendency to accept the proton. They will be accept the protons. Okay. Protogenic, genic means produce. These solvent have a tendency to produce proton, hence they can donate. So here accept protons. Accepts proton. Those solvents accept protons are called as the protophilic solvent. Those are produce and donates protons are called as protogenic solvent. Example is a water or your liquid HCl or acetic acids. These are the protogenic solvent. This is acetic acid. Now amphoteric solvent. Those solvent which can be accept proton and the donate proton. The solvent can be accepts and donates protons are called as amphoteric solvent. Just like the water, alcohol, ammonia are the example. They have a tendency to donate as well as accept the protons. They have tendency to donate as well as accept the protons. Aprotic solvent. Aprotic solvents are not a protophilic solvent or not a protogenic. They are not protophilic, means donate proton, and nor protogenic, means they neither donates proton or neither accept protons, are called as a aprotic solvent. Example is a benzene, carbon disulfide or CCl4 are called as a aprotic solvent. Remember, the solvent is of four types: protophilic solvent which accept the protons, protogenic solvent which will be produced and therefore donates the protons, amphoteric solvent which donate as well as accept the protons, An aprotic solvent which neither donates or not accept the protons, for example benzene, carbon disulfide or carbon tetrachloride. So water is a amphoteric nature. Water has an amphoteric nature, means it is an amphoteric solvent. So how the amphoteric solvent of the water now we consider. Now in the last lecture we considered that according to your Lorry and Bronsted theory, according to your Lorry and Bronsted theory, if HCl is reacted with the water and if ammonia is reacted with the water. Now by using this theory we can explain the amphoteric nature of the water. So when water is reacted with HCl, where HCl is the acid. So as HCl is an acid, according to Lorry and Bronsted theory, the proton donor are acids and proton acceptors are bases. So according to Lorry and Bronsted theory, proton donor are acids and proton acceptors are bases. So here HCl is acid because it will be donates the proton. Water will be accepted, so it is a base. So when HCl can be donate the proton, it has a Cl minus, and water can be accepted, it forms the hydronium ion. It is called as a hydronium ion. It observed that actually when in case of the acid, the hydrogen is not remain as it is. It always combine with the water and forming the hydronium ion. But for our convenience, we can write HCl or any acid can use H plus ion like this way. But actually the H plus ion will be not like this way. The H plus ion is always in the form of the hydronium ion. So similarly here water is act as a base. But when water is reacted with the base, it acts as an acid. Let us consider this example. When ammonia is reacted with the water, here ammonia is a base, so it accepts the hydrogen from water. And when it accepts the hydrogen, it forms NH4 plus and the remaining is OH minus. So like this way, water shows amphoteric nature. It acts as an acid as well as base. It acts as acid as well as base. When it reacted with the base, it acts as acid. When it reacted with acid, it acts as a base. So this will indicate the amphoteric nature of the water. So like this way, we consider the amphoteric nature of the water. Now, the next point is the ionizations of acids and bases. Ionizations of acids and bases. So we consider the acids HCl, H2SO4, HNO3, HBr, HI. These acids, when dissolved in water, they can be completely ionized. So therefore, they called it as a strong acids. So they are the example of strong acids. When you consider example as a NaOH, KOH, when they dissolve in water, they completely dissociated. Hence, they are example of strong bases. But when you consider the example such as the HCN, H2CO3 carbonic acid, or HF, or formic acid, acetic acids, they are the weak acids because when they are dissolved in the water, they will be partially dissociated. They are partially, the dissociation is occur partially, so therefore they are called as a weak acids. Similarly, if you consider example as a ammonium hydroxide or FeOH thrice, CuOH2, aluminium hydroxide. If you consider all these examples are also the example of weak bases because they can be partially dissociated. So depending upon the dissociations of the acids and bases, they are either strong acids, strong bases. If they are partially dissociated, they are weak acids and weak bases. So like this way, you can consider the ionizations of acids and bases. So as weak acids are partially dissociated, so therefore, so dissociations of dissociation of weak acids and bases. Now let us consider dissociations of weak acids and bases, because in case of the strong acids and strong bases, the degree of dissociation is 1. They are completely dissociated. But in case of the weak acids and weak bases, as they are partly dissociated, we can consider the degree of dissociation and dissociation constant. So let us consider acid Ha. Let us consider acid Ha as a weak acid. It is a weak acid. So when Ha acid, when dissolved in water, it gives H plus and A minus. So by applying the law of mass action, K is equal to concentration of the product divided by concentration of the reactant. By applying the law of mass action, the law of mass action gives it is a ratio of concentration of the product to the concentration of the reactant. So product have H plus ion, A minus ion, reactant have H. So like this way, as it is a here the constant which I use for this is called as a dissociation constant for acid. So K is a dissociation constant for weak acid. So dissociation constant of the equilibrium constant which I use for acid is a K, and that is called as a dissociation constant of the acid. Similarly, if you have the base BOH, it can be dissociated as B plus and OH minus. So applying the law of mass action, B plus OH minus, remember we can consider here the partial dissociation as they are dissociated partly. So like this way you get a BOH. So this constant is for the weak base, so I can say Kb. So it is a Kb is a dissociation constant for weak base. So like this way, the dissociation constant for acid Ha, where H for acid, hydrogen, A for H. So for weak base, we can indicate BOH, and it gives a dissociation constant for Kb. So the equilibrium constant which are used for acid is called as the dissociation constant of weak acid Ka, and the dissociation constant for the weak base, it is a Kb. Okay. So now next we consider the Ostwald's dilution law. Next is the Ostwald's dilution law. So this law gives a relationship between alpha and the dissociation constant of acids and bases. So it gives the relationship between acids and dissociation constant of acid and bases and alpha. So let us consider for weak acid. Let us consider this law for the weak acid. The weak acid consider is a Ha. So let us consider 1 mole of weak acid Ha dissolved in V dm cube of solution. Dissolved in V dm cube of the solution. So Ha, it can be dissociated as H plus and A minus. So as we are considering the 1 mole of the weak acid, so initially as there is a no dissociation, so number of moles of the products are 0 because only reactant is present initially. But when equilibrium is attained, at equilibrium, the number of moles present are at the equilibrium, the number of moles present. So for this we consider that alpha is the degree of dissociation. Degree of dissociation. So degree of dissociation indicates the amount of the number of moles of the ions which are dissociated out of the total moles. Okay. So if alpha is the degree of dissociation of H plus and alpha is the degree of dissociation of A minus, then the number of moles which is undissociated is 1 minus alpha. Okay. So similarly, we can consider equilibrium concentration. The equilibrium concentration, it is written in mole per dm cube is, so as, so alpha is the degree of dissociation of the acids. So the when HA will be dissociated, H plus ion will be used alpha as a degree of dissociation, A minus ion gives alpha as a degree of dissociation, and out of the 1, so alpha is gone, so 1 minus alpha is remain undissociated. So equilibrium concentration will be here is a number of moles, here is alpha. So we know that concentration is considered as a number of moles divided by volume. So at equilibrium we consider this concentration, so it is called as a equilibrium concentration. So equilibrium concentration is a number of moles divided by volume. Here the number of moles for H plus ion are alpha, its volume we consider as V. Number of moles here is alpha, the volume is V, and here 1 minus alpha divided by V. We also know that 1 upon V is the C, that is the concentration. 1 upon V, so reverse of the volume is the concentration. So I can write alpha into C, and 1 minus alpha into C. So these are the equilibrium concentration at the, okay. So now let us substitute the values. So according to the, we know that if HA can be dissociated, it gives H plus and A minus. And according to law of mass action, K is equal to concentration of the product divided by concentration of the reactant, and the constant we are used here is a dissociation constant of the weak acid Ka. So let us put up these values here. So value of H plus ion is alpha into C. Value of the A minus ion is alpha into C. The value of HA is a 1 minus alpha into C is equal to K is a dissociation constant. So solving this, so K is equal to alpha square, this one C is gone, into C divided by 1 minus alpha. Now we know that alpha is a degree of dissociation for the weak acid. So weak acid is already very less dissociated. So we can call it 1 minus alpha. This value is very less, and therefore we can't count it as a 1. So therefore K is equal to alpha square into C. Okay, so this value we can consider. So now as K is equal to alpha square into C, now I can write here. So K is equal to alpha square into C. So alpha square is equal to K upon C. So alpha is equal to under root of K upon C. So alpha degree of dissociation, it is a inversely proportional to the square root of its concentration, or alpha is equal to K into V, because 1 upon C is the V. So what is the Ostwald dilution law for the weak acid? So the degree of dissociation is a inversely proportional to the square root of concentration, or degree of dissociation is a directly proportional to the volume. So that relationship is given and by the scientist Ostwald's, so it is called as a Ostwald's law of the dilution law. Okay. Now similarly, we can also consider it for the weak base. Similarly consider for the weak base. So let us consider for the weak base as a BOH. Now consider the same law for the weak base. It also gives a relationship for weak base. So now weak base we consider 1 mole of the weak base. Now we consider as a BOH. It's a dissolving VDM cube of the solution, where alpha is a degree of dissociation and Kb is a dissociation constant. Okay. Now similarly consider if the BOH is the 1 mole of the BOH when dissolved initially. So as the only reactant is present, the product's number of moles are not there. So it is a 0, 0. So when the equilibrium is attained, so out of the 1 mole, alpha is the degree of dissociation. So it indicates that out of the 1 mole, alpha is the number of moles which are dissociated for the BOH. Then 1 minus alpha is remain undissociated. So at the equilibrium again, So concentration can find out, that is called as equilibrium concentration, and that concentration in mole per dm cube. So number of moles are alpha alpha and the volume is given as VV. So I can write equilibrium concentration as a alpha divided by V, alpha divided by V, and 1 minus alpha divided by V. We again know that inverse of the volume is a concentration. Okay, so they can I write, so 1 minus alpha into C, alpha into C, alpha into C. I put up these values in the same formula we I consider for the base. So instead of K, now I use K. So again, BOH is a base which can be partially dissociated as B plus and OH minus. So therefore, Kb is equal to H plus here. So Kb, I get value here. So it is like this way. The same relationship I obtained as same for the acid. Okay. So I again say that. So as BOH can be partially dissociated, the dissociation constant Kb is equal to concentration of the product into concentration of the reactant divided by BOH. So substituting again the values from this chart. So this value is alpha into C, 1 minus alpha into C. Okay. So therefore Kb is equal to alpha square C divided by 1 minus alpha. Okay. So as base is a very weak, degree of dissociation is again a fraction quantity. So we know that degree of dissociation is what? Is a fraction of total number of moles of the corresponding substance which is dissociated at the equilibrium, and this quantity is very less, and as less quantity we are subtracting from 1, so you ultimately get a value is near about 1, and therefore I write here is 1. So alpha square into C is 1 minus alpha. I put this value as 1, so therefore I get relationship Kb is equal to alpha square C. So alpha square is equal to Kb divided by C. So alpha is equal to square root of Kb divided by C, or alpha is equal to square root of Kb into V. So again, so from Ostwald dilution law, we can write one statement is that the degree of dissociation for weak acids and weak bases are 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 inversely proportional to square root of its concentration and directly proportional to square root of its dilution at equilibrium. So degree of dissociation for weak acid and weak bases are inversely proportional to square root of its concentration or directly proportional to the square roots of its volume at the equilibrium. So this is the Ostwald's dilution law for the weak acids and weak bases. Okay, thank you.